Hello gentlemen, welcome to our video on section 10.8 on molecular diffusion and effusion. Now you may have heard of diffusion before. Diffusion is the spread of a substance throughout a space or throughout a second substance. Now an example of diffusion would be something simple. Let's say we have air freshener, we spray it in the air, and eventually it will leave this concentrated place and diffuse outward and spread throughout the room, making the entire room smell like lavender. Now, what does the diffusion rate depend on? It depends on the temperature of the room and the identity of the gas, the identity of the mixture of chemicals in that particular air freshener. Now, you have to remember, temperature is a measurement of the average kinetic energy of particles. So the average kinetic energy of those air freshener particles is based on the temperature of the room. And kinetic energy can be defined as 1/2 times the mass of that substance times the velocity squared of that substance. So, diffusion depends on temperature, temperature depends on kinetic energy depends on mass and velocity. So let's say, for example, I have two different samples here. I have lavender air freshener, I spray it. At the same time, I spray Kenneth Cole black. Get it, gentlemen? So Kenneth Cole, I spray this cologne, and I ask you this question. If I spray them at the same time, which one reaches you first if you're in the back of the classroom? Well, they're at the same temperature right now, so they have the same kinetic energy. Remember, if they're at the same temperature, temperature is the measurement of the average kinetic energy. So that means they have the same kinetic energy as well. But does that mean they have the same velocity? They have the same temperature, same kinetic energy, but does that infer that they have the same velocity? Maybe, maybe not. Let's check it out. So, kinetic energy of the air freshener is equal to the kinetic energy of the cologne because they are at the same temperature. So that means 1/2 M1V1 squared, this is of the air freshener, I put the ones here to represent air freshener, and is equal to 1/2 M2V2 squared. Now, let's just say, I'll give you the answer, the air freshener gets to you first. Then what does that mean? If the air freshener reaches you first, that means it had a faster velocity, right? This V here was higher than that V because it reached you first. In order to keep this side of my equation and that side equal, the same value, if this V is large, that must mean this V was smaller. Okay, but that doesn't give me equalness on each side. That must mean that this mass had to be smaller, and this mass was larger, meaning the air freshener reached you first in the back of the room because those gas particles had a smaller mass. With a smaller mass, they can have a faster velocity and get to you. So, if it has a higher velocity, it means that it had a smaller mass. So the mass and velocity in these individual equations are inversely proportional. If you have a high velocity, you have a lower mass than the other particles that you're comparing yourself to. This substance has a higher mass and a lower velocity. This is when both substances are at the same temperature, the constant temperature. Okay, that's diffusion. Effusion, similar, but some slight differences here. Effusion is the escape of gas particles through a tiny hole. For example, in a balloon, you've all had balloons before. You blow them up on someone's birthday, and you leave them in the corner, and over a few days, the balloons start to deflate. And you go, well, how is that possible if, there's no hole in the balloon? Well, there are small, microscopic holes in that balloon, and air particles can find their way out of it. So let's say I give you this example. I have two balloons with different gases in them. The gases have different masses because they are different substances. I poke identical holes in each balloon. and each balloon is at the same temperature, room temperature. And I ask you this, which gas will effuse faster? Which gas will leave that tiny hole in the balloon faster? What's the answer? Right, the one with the smaller mass. The one with the smaller mass will effuse faster. Smaller mass usually means smaller volume. You can get through that hole much quicker and at a more frequent rate. But now, second question, how fast? Now that's a different question. And to that, we look back on our relationship between kinetic energy. So if they're at the same temperature, that means they have the same kinetic energy. Ke of the first gas equals Ke of the second gas in the second balloon. And again, we have this relationship. 1/2 mv squared of the first substance equals 1/2 mv squared of the second. Now what we're going to do is actually use a little algebra to our advantage. We're going to rearrange to compare the masses and velocities, meaning get mass and velocity on the same side. If I rearrange this equation algebraically, I can get my velocities on the same side like this, dividing both sides by V2. And I can get my masses on that side together through division. So now I have a ratio of velocities to masses, how they compare to one another. Now I can take the square root of each, because I want to look at the velocity, not the velocity squared, of each side, and then I get this relationship here. This is a very important equation. That's why it's boxed. You might want to take note of that. But this tells me the ratio of speeds in relationship to the square root of the masses of those gases. So if I know the identity of those gases, then I know the masses, because when I say mass here, I'm referring to molar mass. Since I know the molar mass of these gases, then I can determine the ratio of their velocities, and I can determine, if I know one velocity, I can determine how fast a single gas is going. Now this equation reflects a law. The law that it reflects is a law called Graham's law. It essentially says in words what that equation says. The effusion, or that equation can also apply to diffusion. So the effusion or diffusion rate of a gas is inversely proportional to the square root of its molar mass. The lighter gas has the higher effusion or diffusion rate. So the gas with the lower molar mass will move faster. It will diffuse or effuse at a quicker rate. Gentlemen, take notes, come prepared to do a little practice with this next class. Adios.